Your media server pod OOM-Kills every 15 minutes during a 200-person webinar. Memory spikes to 4 GB, then crashes. You assume a WebRTC memory leak, but the real culprit is forwarding all 200 video streams, each consuming 50 MB of buffer. That's 10 GB in a 4 GB container. Here's exactly why. Welcome to TheCodeForge. Before we dig into that production issue, let's cover Design Zoom. Zoom is a real-time video conferencing platform. It uses a selective forwarding unit, SFU architecture, where the server forwards selected video streams to each participant, reducing client processing. Key components include a signaling server, WebSocket, media server, SFU, TURN server for NAT traversal, and a distributed backend for rooms and users. Before you write a single line of code, you need to pick your media routing strategy. The two main options, MCU multi-point control unit and SFU selective forwarding unit. MCU mixes all incoming streams into a single composite stream on the server. Each client sends one stream and receives one stream. Sounds simple. But the server has to decode, mix, and re-encode every stream. That's CPU intensive and adds latency. SFU, on the other hand, forwards streams without decoding. The server is just a smart switch. It selects which streams to send to each client based on who's speaking. The client decodes multiple streams and renders them. This shifts the processing burden to clients, which is fine for desktops but tough for mobile. However, SFU scales linearly with participants, O(n) server load, while MCU scales O(n)2 because the server must process every combination. For a 100-person call, MCU server does 100 times the work of SFU. That's why Zoom uses SFU. Here's the bandwidth math. For SFU, each client sends one stream and receives M streams from active speakers. Total server bandwidth is N times the sum of uplink and M downlinks. For MCU, each client sends one and receives one mixed stream, but server CPU is O(n)2 because it must process all combinations. So for 100 participants, SFU server bandwidth is 1 Gbps, while MCU server CPU is 10,000 stream combinations. The decision: use SFU for more than 10 participants. Before any video flows, clients need to exchange session descriptions and ICE candidates. This is signaling. You need a reliable, low-latency channel. WebSocket is the standard. Each client connects to a signaling server, typically a separate service from media servers. The signaling server handles room management, user presence, and relays SDP, offers answers and ICE candidates between clients. Here's the signaling flow in pseudocode. Client A connects, joins a room, gets the list of existing peers, then creates peer connections and exchanges SDP offers and answers through the server. The server validates authentication and SDP size and forwards messages. This ensures low-latency setup. The media server is the heart of your Zoom clone. It runs an SFU that receives RTP packets from publishers and forwards them to subscribers. Each media server handles a subset of participants. Key components: a transport for each peer, a router that maps incoming streams to outgoing streams, and a bandwidth estimator. The SFU must support simulcast. Each publisher sends multiple resolutions. The SFU selects which layer to forward to each subscriber, based on their bandwidth and screen size. Here's a simplified SFU implementation. It maintains a map of rooms, each with producers and consumers. When a new producer joins, it notifies all consumers. The forwarding logic selects active speakers based on audio levels and forwards their high-resolution streams, while others get low-resolution or no video. This is the core of efficient video distribution. A single SFU can handle about 100-200 participants. Beyond that, you need to distribute the load. For a 1,000-participant room, you might have 10 SFUs each handling 100 participants. They are connected via a media bridge that forwards active speaker streams between servers. A global audio-level aggregator determines the top speakers, and only those streams are forwarded across servers. Here's the distributed SFU architecture. Each SFU has a bridge module that forwards selected streams to other SFUs. Global active speaker detection is done by a central service that collects audio levels from all SFUs and returns the top 6 speakers. This ensures only necessary streams cross between servers. Real-time video is unforgiving of packet loss. WebRTC has built-in bandwidth estimation, GCC, that adjusts bitrate based on delay and loss, but you need to configure it properly. The SFU should also participate. It can send REMB messages to publishers to reduce their bitrate. For clients with poor connectivity, the SFU can switch to a lower simulcast layer or drop video entirely. Here's a server-side bandwidth manager. It collects receiver reports from all consumers of a producer, computes the minimum available bandwidth, and sends a REMB message to the producer to reduce bitrate. If packet loss exceeds 5%, it switches the consumer to a lower simulcast layer. This ensures smooth video even under poor network conditions. Not all clients can establish peer-to-peer connections due to symmetric NATs or firewalls. That's where TURN comes in. TURN servers relay media traffic. They're bandwidth hogs. Each stream consumes relay bandwidth. You need to deploy TURN servers in multiple regions close to users. Use ICE to try direct P2P first, via stun, then fall back to TURN. Configure TURN with authentication, time-limited credentials to prevent abuse. Here's a TURN server configuration using CodeTurn. It listens on ports 3478 and 5349, uses time-limited credentials, and limits bandwidth per user. On the client side, ICE servers include both stun and TURN. Monitor the relay ratio. If it exceeds 20%, investigate NAT issues. Recording a Zoom call is harder than it looks. For compliance, you need per-participant recordings. Solution: have the SFU send each participant stream to a recording service. The recording service can either store individual tracks for later compositing or mix them in real time. For real-time mixing, use a dedicated MCU-like component. Better, store individual tracks as fragmented MP4 with timestamps and composite offline. Here's a recording service that writes each participant stream to a separate file. For composite recording, you can use FFmpeg to mix streams offline. This approach handles network glitches by buffering data. Building a Zoom clone is a massive undertaking. You need expertise in WebRTC, networking, distributed systems, and media codecs. If your core business isn't video conferencing, don't build it. Use a third-party API like Twilio Video, Agora, or DailyCo. They handle SFU, TURN, and scaling. Only build if you have specific requirements: custom UI, offline recording, proprietary codecs, or air-gap deployments. This is the same issue we highlighted at the start. Here's exactly why that happened. The SFU was configured to forward all video streams, not just active speakers. Each 720p stream at 30 FPS consumed about 2 Mbps bandwidth and 50 MB memory for buffering. 200 participants times 50 MB equals 10 GB, but the container limit was 4 GB. OOM-Killed did its job. The fix was to enable simulcast and forward only active speakers. We set max video streams per client to 4, the 3 loudest speakers plus self. Memory dropped to 800 MB. No more OOMs. The key change was limiting active video streams to a small number. If you forward all streams between SFUs, you'll saturate your inter-SFU link. In a 1,000-person call with 10 SFUs, forwarding all 1,000 streams would require 1,000*2 Mbps equals 2 Gbps per SFU. Only forward active speakers. Use a hard limit of 6 streams per SFU. Some tutorials show signaling over HTTP long polling. Don't. The latency kills the ICE negotiation window. WebSocket is mandatory. I've seen a team lose 30% of call setups because ICE candidates expired before the HTTP response came back. I've seen production configs with hard-coded TURN credentials in the client code. Attackers can use your TURN server for free relay, costing you bandwidth. Always use time-limited credentials generated by your signaling server. CodeTurn supports REST API for this. The article assumes modern WebRTC, e.g., simulcast, REMB. However, older browsers, Safari 14, iOS 14, 5, lack simulcast support. For production, detect client capabilities via RTC RTP sender, get capabilities, and fall back to single stream or transcoding if needed. The article mentions active speaker detection, but doesn't show how to implement it. Use WebRTC's RTC RTP receiver, audio levels, or the get stats. API to retrieve audio energy per stream. The SFU can then select the top end speakers by comparing levels. The article covers OOM from too many streams, but another common issue is memory leaks from unclosed peer connection objects. Always implement a health check that periodically closes stale connections, e.g., no RTP for 30 seconds, and monitor RTC peer connection, count via metrics. Here's how to debug common issues. For OOM kills, check pod logs. For packet loss, use SSS. For bandwidth estimation, check WebRTC stats. If turn bandwidth is saturated, scale horizontally. Let's run through some common interview questions. How does Zoom handle poor network? Uses simulcast, REMB, and layer switching based on packet loss. How to detect active speakers globally? Each SFU sends audio levels to a central aggregator every 100 ms. What happens when turn runs out of bandwidth? ICE failures. Mitigate with load balancing and client fallback. And a few frequently asked questions. How does Zoom scale to 1,000 participants? Distributed SFU with media bridge and global audio level aggregator. What's the difference between SFU and MCU? SFU forward streams without processing, MCU mixes on server. SFU scales better. How to set up a turn server. Use TheCodeForge, configure ports, time-limited credentials, and monitor relay ratio. Key takeaways: SFU scales better than MCU. Never forward all video streams. Use WebSocket for signaling. Deploy turn servers with time-limited credentials. These principles will help you design a robust real-time video system. Ready to go deeper? Up next, design Google Maps, then design Airbnb, then design a digital wallet. Find them all at TheCodeForge.io. Thanks for watching. The full article and code examples are covered in detail at TheCodeForge.io.